So let's try and see if we can think through this a little bit more, and in particular use what we learned in the previous theorem. So let's name this parallelogram A, B, C, D. We know that it's parallel because these opposite lengths are parallel because it's a parallelogram. We also know something else from the previous theorem, the OSA theorem, that the opposite lengths are also congruent. So the opposite lengths are not only parallel, they're also congruent. Okay? And now what we're going to do is draw this, whoops, I'm going to try to do a slightly better job of this. Draw a diagonal through, what am I doing? That's terrible. Let's try that one last time here. Draw a diagonal through the object like so, and then draw one more diagonal this way like so. Okay, and I'll call this point here in the middle E. Those are supposed to be straight lines here, but my handwriting's a little bit off today. All right. Now looking at this picture, we also know a few other things as well. We know that these angles up here are congruent to each other by their alternate interior angles, and so are these angles over here. Okay, and well, I think that's actually good enough for us right now in order to do our work. So what we're going to try and show is that the triangle on the top here, triangle ABE, is in fact congruent to triangle CED. So these two yellow triangles that I am obnoxiously shading in here, those are in fact equal to each other. And it's not hard to see why. We know that the opposite lengths are equal to each other. AB is congruent to CD. This was from before the OSA theorem, opposite sides and angle. We know that angle BAE is congruent to angle DCE. They're alternate interior angles with parallel sides. Okay, and we also know angle EBA is congruent to angle EDC, really for the same reason. So now we have a side, we have an angle, and we have an angle. So again, two angles and one side is enough for us to conclude that triangle BAE is congruent to triangle DCE by angle, side, angle. Now that's not the only method that we could use. There's some other ones. We have a vertical angle in there as well, but this is sufficient for us to prove that. And now because the triangles are congruent, then we could take this a step further and we can say that these side lengths must be congruent. CE and AE must be congruent. So CE must be congruent to AE by CPCTC, and BE must be congruent to DE. Really for the same reason. All right. So let's name this theorem something as well. This says something about if you notice here, the diagonals, they cut each other in half. So we'll call this the diagonals are bisected theorem. Okay. In other words, the DAB theorem, the DAB theorem. Okay. Diagonals are bisected. So using the DAB theorem, we can now look at this picture and solve these problems quite quickly. We can say that 9 is equal to 2n minus 1. Add 1 to both sides and divide by 2. So 5 is equal to n. And we can say that m plus 8 is equal to 3m. subtract m from both sides, and divide both sides by 2, and we get that 4 is equal to m. Okay, and there we go. Once we have this theorem in place, the DAB theorems, diagonals are bisected, then solving these types of equations are relatively simple. There is one more problem in this lesson, and if you work through these problems, perhaps you may discover yet another new theorem, but I will leave it to you to work through this. Ask for help as always if you need it. Thank you for watching, and have a wonderful day.